Yes.
Yeah. So first of all, the course duration is 4 months, and here in these 4 months we will cover both standard cell layouts and analog layouts, and some portion of memory layouts. That's it. And again, before starting these analog layout and standard cell layouts and memory layouts, the basic classes were, it is about analog electronics, and next one digital electronics, and there are few classes on Unix, and after that I will start the classes which are related to purely layout, and even in the layout classes also, first we will start with the standard cell layouts, because before going to the analog layout, it's better to know the standard cell layout, because standard cell layout will give the complete information on how to draw the transistor manually. Because in analog layout, all the transistors by default coming as a instance. But in standard cell layout, that even that instance also you have to create on your own. So that before going to analog electronics, it's a good thing to exposure about the standard cell layout first. So understood? Hello?
Yes. Yeah.
If you have any question, yeah, if you have any question, then you can ask me. And once if you are done with the standard cell layouts, then we'll start with the analog layouts. And in analog layouts, here the code in the analog layout course, there are different types of analog cells. One is BGR and op amps and LDOs, and all these are with 45 nanometer. This technology we are planning, we are working with this 45 nanometer technology here, and here the advantage with the course is, here we are providing 24/7 tool support, and well experienced faculty, and it's affordable, and the most important thing is 100% placement support. And usually the companies that we are recruiting the candidates are like Synopsys, Western Digital, and Sankalp Semiconductors, and Insemi, HCL, Altran. So many companies are there, and even L&T and Tesalu Semiconductors, Marship, Xilinx, and SmartSock. Like that, so many companies are there. There are multiple companies that almost 200 plus placement companies are there. Definitely in that in the duration of 4 months, definitely you people will recruit in any among these all 200 companies. So any questions till now? And if you come to the salary structures, and once if you are done with your placement, the basic, actually usually for freshers it will be around 4 to 6 lakhs, and if you get 3+ years of experience, it will be around 12 lakhs, 12 to 15 actually. It depends on company to company. And once if you get 5+ years of experience, it will be 25 to 30 range. And 5 plus experience means it's similar to the lead position. And if you get manager position, then it will be around 50 to 70 lakhs. Understood? Any questions now till now?
Sir, only 45 nanometer or any FinFET technology available is there?
Till now, FinFET is not there. Till we are supporting 45.
Present is using only FinFET technologies, right? Again,
No, see, FinFET, don't think like that. I mean, entire industry is working on FinFETs because there are so many companies that are working on even higher nodes compared to the 45 also. Because FinFETs are usually used for lower voltage applications only. But once if you are dealing with the higher volts, then FinFET won't support right that much voltages. You have to go to the higher nodes only. Like if you come to the PMIC chips, something like these kind of higher nodes, we have to go with at least 90 nanometers or 130, sometimes even 180 also. FinFETs won't support that much voltages.
that's
Understood?
sir, that's fine, but
Uh,
again, I want to learn FinFET after completion of this 4 months. I want to learn FinFET also, right?
See, one thing, just remember one thing. Before knowing, without knowing all these basic standards of the layout and all about the conventional MOSFETs, and I'm sure definitely you won't understand of the FinFET layouts.
Okay.
Because conventional mass is the basic mass.
Okay.
From where FinFET came, right? From the basic conventional mass only, right?
Yeah.
So if you don't know the basics of this conventional mass, how can we understand that FinFET layouts? The difference between the FinFET layout and normal layout is the only of the fins. Actually, in conventional mass, we have only gates over the oxide. But in FinFET, the oxide will come as a fin structure. I'll show you that cross-sectional view also, FinFET, and I'll let you know the differences between conventional mass and FinFETs. Okay.
Okay.
Apart from some differences, I think most of the things will remain same, right? I mean, this
Yeah,
is
most
layout.
of the things will be same. Once if you know the basic conventional mass layouts, then it is very easy to understand with the FinFET layout also. Even for me, while I'm in my initial career, we don't have FinFET layout also. FinFET devices also itself that was not at all there. Then, but now we are able to working on FinFET layouts, right? Don't go into that dilemma. Like if you know the FinFET, then only we can do the layout of FinFET. Don't think like that. The basic thing is, if you know the basic layouts, then everyone can do the FinFET layouts. But if you know only FinFETs, I don't know whether you can people draw basic conventional CMOS layouts or not. Understood, right?
Oh, yes, sir. Yes.
So, any doubts now? Okay.
I have one doubt.
Yeah, still.
Yeah. So in this course, the title itself is basically on the layout, right? So
Yes, exactly.
So I presume that the schematics will be given, and the emphasis will be more on the layout.
Yes.
I was just curious whether we would also cover the simulation of the layout.
Simulation, yeah. For layout wise, you people will have physical verification tools like DRC, LVS, and everything. But schematic wise, tell me.
Yeah. So okay, I'll tell you the question that I am trying to get more clarity on.
Actually,
so
I just want to explain this. Actually, talking about the after post layout simulation.
No. Layout means it's purely related to the pre-layout simulations only. But post-layout simulations, all those will taken care by the designers.
Sir, excuse me. Let me complete. Hello.
Yes,
Our
tell me.
layout giving the properly or correctly working or not, so we have to go for the post layout simulation, na? So
Right.
after post layout simulation, we will be able to know that it's correctly it's working, and that's how much it's efficiently giving, because whatever the schematic giving the outputs, obviously layout you will not give the that's much efficient output. There will be some degraded output, but how much it's degraded, how it will be, so we have to go for this, na? That's the things.
Yeah, see, wait, just guys, wait. See, thing is, the intention of the layout course is to expertise in the layout, right? To expertise you guys in the drawing the layout. See, if you take 5 years of experience guy and if you take 1 year's experience guy, definitely there will be some difference drawing the layout for a particular circuit. So, and if we come to the post layout simulations, that is purely it's a designer will run the post layout simulations and he will come to us. Like if he find any something, if he didn't meet particular specs and all, if he will come to us, then he will let us know, like here I am not meeting the constraints, so we have to change these layouts. He will let us know. So based on those, we need to change our layout, and that is the actual process in the company is going on. But thing is, it doesn't mean like you no need to know anything, any layout basics. Simply blindly I will draw the layout, and if something came from designer side, he will come to us and he will let us know. Don't think like that. But thing is, you have to understand the basics of layouts. How to, what are the techniques that we need to use to get the good quality layout. So after that, designer will simulate that layout. So most probably, definitely it will. If you follow all the layout guidelines, definitely it will come clean. But if for any some critical circuits like ADC or BGR circuits, there will be some slight iterations will come. You understood, right?
Okay. So I have a pretty basic question. I mean, I totally get it because I come from a similar background. So
Okay.
my intention of this course is getting more familiarity with the Cadence tool itself. Okay.
Yeah,
So
definitely you will get.
no, I mean, when you mentioned about the post layout simulation,
Yes.
can we at least expect, let's start with a simple inverter,
Yeah.
CMOS
See, that thing
inverter.
will be there. See, even for the first class itself, we'll show
Mhm.
you how to simulate the circuit. But thing
Right.
is, our main course intention is to expertise you guys in the layout drawing. Correct, right?
Okay. No, that's okay. I mean, that's
Uh,
obvious. But if you
hmm.
could teach us, how to simulate it,
Yeah,
then,
that will be there by default. See,
okay.
that will be there for the initial schematics, but it doesn't mean like for each and every
No,
schematics
no, 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 no.
we need to run simulations. It
No,
not
no, no.
required. First thing is,
Right, right, right. But at least the
yeah,
how to
that
do
will
the
be there in
simulation,
curriculum.
that will be covered.
See, in curriculum itself, that is there already.
Okay. Okay.
Okay.
That clears it. Yeah.
Yeah. So and also here we will provide course material also, and even 24/7 tool support. You can log in any time if you want. Then you can practice your layouts. And if you have any question, then you can ping me in the online WhatsApp or something.
Sure.
Okay. So this is about the course structure
One,
and
one,
course
one, one,
duration.
one question I have. I'll directly go to one particular question. Suppose
Yes.
I mean I have experienced it. So suppose if schematic is given and we give the layout and the designer comes and says, okay, on this and this node, on suppose MOSFET drain node resistance is very much than expected. So how to reduce that and techniques of that, or how to reduce the cap on certain node while giving up cap on some other node. So like these techniques I'm expecting. So would it be there
Yeah.
like
See, first thing is, guys, the difference between the layout and schematic is it's a only in the tool designer will draw designers will use some symbols and wires and he will complete the design. But the practical in industry in fabrication, people will go with the layout only, right? They will take the layout database and they will fabricate the chip accordingly the layout.
yeah,
Thing is
but
one.
yeah,
Yeah, wait,
just
just I'll come to that point. So whenever if designer come to us and he told like this node I am seeing more resistance or this node I am seeing more capacitance. So thing is if the particular node is seeing more resistance means particular signal, then we need to reduce that routing length, or otherwise we need to increase the signal width, or otherwise we need to go to the top level metal. You understood, right?
Yeah.
Based on the feasibility, like based on the situation that whatever we have in the current layout, let's say if you don't have any area, understood, right? So then the ultimate solution is you have to go to the top level metal. Then top level metal means that for the top level metal, obviously the gap and resistance will be very less compared to the lower level metals. But let's take one more example. Like if you have more area and if you have sufficient area, then thing is you have to try to reduce that routing length. You need to place the blocks in optimum manner. Like let's say if you have two inverters, the output of first inverter is going to the gate of the second inverter, but you just kept one inverter at extreme left and you just kept one second inverter at extreme right. That is not a good placement, right? You have to place both inverters nearby each other. Then these are some simple layout techniques that all these techniques will come with some practice.
Okay, so basics of it will be covered, right? I mean, so if
Yeah,
we come
everything will
across a
cover.
problem, yeah,
Yes.
so we'll be able to like go for we'll be able to like suggest some solutions or like that, like you discuss some of these. So
Yeah,
that like
see
this,
one
yeah.
thing. See, first thing is once if you're done with the layout of BGR, then you people will get to know all the basic things.
Okay,
Because
got it.
band gap reference is a critical circuit there, and also they, if you're done with the ADC, then then you people will get to know what is the importance of this matchings and what is the importance of signal symmetrical routings. All these
Got
things
it.
will come, and what is the importance of shieldings. Okay,
Yeah, got it.
so clear, right?
Yeah, clear.
Yeah. So okay, shall we discuss some few basic topics like CMOS fabrications and basics of Linux and some reliability checks of layout. Okay.
Yeah, yeah.
Yeah. So
Okay.
any question till now?
No.
Hello. Yeah. Okay. Then let's start with some CMOS fabrication. See, guys, see, this is a demo class. So here we'll cover basic things. But once if we start the regular classes, we'll go in depth. Okay. Hello.
Okay, sir.
Yeah, okay, sir.
Got it.
Yeah, for CMOS fabrication, this is conventional CMOS. So thing is, let us take one NMOS transistor and PMOS. So you know what is the difference between NMOS and PMOS, right? So usually this NMOS will get if we dope intrinsic silicon with fifth group elements, and if we dope in intrinsic silicon with third group elements, we'll get P-type MOS. That you know, right?
Yes.
Yeah. So now actually the process of this fabrication CMOS fabrication will start with the silicon wafer preparation. The first step is silicon wafer preparation. So here silicon means it's a sand, right? We'll take pure sand and we'll boil with we will boil this pure silicon around at 1200 degrees centigrade temperature. Then this entire silicon will form as it will get some liquid form. So and in next one they'll use some sizzle process. There is one process that name is sizzle process. So here, see, this is the liquid sand. Here we have liquid sand. And that robotic machinery, it will be like this. Some circular shape will be there. And here some, this is some machinery, and it will rotate something like this. This machinery will continuously, it will rotate like this. And once, if you remove this machinery, and if you print those structures, like here all these liquid sand will attach here, right? So if you print this one here, you will get circular kind of structures. These kind of structures you will get. This is a wafer, silicon wafer. Understood, right? Hello?
Yeah.
Yeah. So now, and if we come to the next one, so once if we get the wafer, this is a wafer, and among one single wafer, there will be thousands of millions of transistors, not even thousands, millions of transistors will be there. So this is one transistor, this is one transistor, something like this. So now let's come to one particular transistor. Now, if we go to the cross-section view of this transistor, CMOS transistor inverter, let's take one wafer. This is a silicon wafer, and we need some substrate, right, from the silicon wafer. Let's say if I want to prepare one CMOS and inverter, the global substrate, it is a P-sub. Now what I will do is, I'll take this substrate and I will dope with the third group elements. Then I will get one P substrate, global substrate. And now we have one P substrate, and we need to prepare NMOS and PMOS. And guys, remember, this is NL process. NL process means the PMOS will fabricate in dedicated NL, and NMOS will fabricate it in global substrate. And let's come to the next slide. So now this is one P sub. And now before going to the diffusion process, the next one is, second process is oxidation. In oxidation, again there are two types. One is dry oxidation, and second one is wet oxidation. The difference between these two is, wet oxidation means, actually here the chemical reaction is, here we will take some H2O and silicon, and using these two we'll do some chemical reaction, and we will get one SiO2. This is silicon dioxide, this is oxide diffusion. And here usually it is in the form of between SiO2, oxygen and hydrogen. With this we will prepare SiO2, and usually this happens at around some high temperatures, like around 1000 degrees centigrade or something. But this is around 700 to 800 degrees centigrades. So, but the main difference between this one and dry and wet oxidations is, wherever if you use dry oxidations, it will give better results in terms of electrical properties, like VT, something like that. Compared to the wet oxidation, we will get some superior electrical properties if you use dry oxidation techniques. So, and the top one more layer is there, right? This is the oxide layer, oxide diffusion, SiO2. This one. So now we have SiO2 and P sub. Now let's come to the photolithography. See, the why we need to use photolithography means, if you come to the previous slide, see, this is SiO2 and this is P sub, right? Here we need to fabricate one NMOS transistors here, and here we need to create one PMOS. For NMOS transistor, the source and drain diffusion is, it's N plus source, N plus drain. Here P plus source, P plus drain. So we need to diffuse this junction, source junction and drain junctions. So, but that's why we need some open at this portion and this portion, and at this portion and this portion, we need some opens to diffuse the source and drain junctions of both PMOS and NMOS respectively. For that one, in order to get these opens, what we need to do is we need to infuse, we need to diffuse some UV rays to remove this portion, to remove this SiO2 portion. But thing is, if you diffuse UV rays directly over this SiO2 surface, something like this, it will create some damages to the SiO2s. You understood, right? What is the uses of photolithography? Hello? Hello?
Yeah,
You can hear me, right?
yeah, I can.
So now the people will take some maskings here. Wherever we don't want the etching process, they will cover with photolithography material, and now they will diffuse UV rays. So thing is, only these UV rays get these SiO2s get affected by UV rays only at this portion. Entire remaining portion is covered with the photo masking materials, so that we can protect the unwanted portion. You understood, right? This will happen like this. I'll show you here. These are the photo masks. Earlier, we'll cover with entire photo mask, something like this, and after diffusing the UV rays, the portion wherever we will not cover with this photo masking material, it will remove completely. It will remove. And here, since this portion is covering with photo masking material, it will not affect by the UV rays. Now we have opens for source and drains of NMOS, and as well source and drains of PMOS. Now the next step is diffusion process. Here, once if we get the opens for this both PMOS and NMOS, they'll use some this is the diffusion process, diffusion space for so these are the diffusions for NMOS and PMOS, source and drains. Now, by using metallization techniques, they'll take one gate contact here and source contact from here, drain contact here. Similarly, source is here, drain is here, and this is the gate contacts. And this is global P substrate. And here they will prepare one N well. This is the base CMOS inverters. Understood? Hello?
Yes.
Hello? Yeah, guys, tell me guys whether you
Yes,
you
yes.
understood or not.
Yes, sir.
Yes.
Okay. So again, after completing this diffusion process and all, again there are few more steps like passivation, packaging. Those are actually this is the core circuitry, but we need to protect this core circuitry through some coating material. That coating material we can usually they will prepare in passivation or packaging techniques. Usually, if you take one IC, the top surface it will looks like a black surface, right? That is the coating. Inside of that one only we will have main chip. Okay.
Yeah.
Okay. This is about basic process of CMOS. And if we come to the basics of some Linux and Unix, see, this is why people are using only Unix software compared to the Windows. Means it's a, but the basic difference between Windows and Linux, Unix is a command-oriented language and it can provide more security compared to the Windows. That all you know, right? And here we need to know so many commands like CP command, LS command. CP command is for copy one file from the other source to destination or something, and make directories mkdir and remove directories rmdir, and to display the contents of a directory we will use ls command. Something there will be multiple commands, like thousands of commands there will be there. And again, in this course only, we'll try to explain about the shell script writings, because usually, see, first thing is I'm not comparing other institutes, but I'm telling the truth actually what is going on in industry in many institutes. So people only tell about these commands only, because actual thing is it is sufficient to know the commands and their functionality to operate with the system, but you should know about the script writings. This will add some extra advantage, extra cushion, because if you know the how to write the scripts and all, then you will get some complete idea about the entire operating system. And even if you know the script writings, you can create your own custom settings to your tool. And this is the basic language. If you know this shell script writing, then it is easy to understand about the skill programming. Skill programming is completely related to the cadence tool. If you know the skill programming, then you can write your own scripts to fasten the speed of layout and all. You can create your own shortcuts. You can create your own bind keys. It is the extra advantage for every layout guy. Understood, right?
So this is covered here, right? I mean, some basics of script writing and all, apart from that common command.
Yeah, see, common commands anyway, it's there in the curriculum. But here, apart from these commands, we will try to teach about the script writings also, especially about the shell scriptings.
Great.
Okay.
Nice.
So, any queries? So, okay, if you don't have anything, then I'll go to the next one. So, if we come to so till now we covered basics of CMOS and basics of Unix and script writings and all, right? So now if we come to the tool, here we will use Cadence tool, Cadence Virtuoso tool. Presently, we are supporting 45 nanometer PDKs. And there is some, and also we are planning to start 28 at least, 28 nanometers. So, and if you open the Cadence tool, I think most of you guys are familiar with the Cadence tool, right? If you have your, if you are coming from post graduation with VLSI background and all. So can I expect? Yeah, no, it's right. It's correct, right? I think you people all might know about how the Cadence tool will looks like.
Yeah.
Okay, and thing is, so I'll come to one point. Like before starting these basics of this demo class, You people asked me how to improve the layout quality, correct, right?
Yes, yes.
Yeah. So I'll tell you one basic thing. Here I have one block. Here we have one more block. From this block, there is one signal going to this input of this signal is going to the second block, and it is connecting here. This is let's say it is A and it is B. So if we route this signal, let's say when one guy has routed the signal 10 microns, and same one more person has routed the signal around 50 microns. Now, compared to displacement, definitely here you can see more resistance and more cap, right? So, and sometimes, let's say if the signal which is coming from A block is connected to the gate of the B block, something here we have one transistor, so it is directly connected to the gate. So, if you increase this routing length, then there is one parameter like it's a antenna effect. So if we increase this gate routing lengths, then you people will get some antenna effects. So you need to reduce this. All these kind of techniques is the reliability techniques. If you don't consider these things, your chip will not work for many years, because this antenna effect will spoil entire your active gate and all. So you need to remove all these things. These things will come into the layout only, because directly designer can't say like here you will get antenna. It purely layout guy responsibility, and this is one reliable technique. And sometimes if it is a more current carrying signal, it is not going to the gate. It is not only going to the gate, it is going to some source and drain junctions, and here there is more current is going on, like it's around 1 ampere or something. Then the basic criteria here you have to consider is you should route this signal with sufficient metal widths. Let's say if to carry this 1 ampere current, the required metal width is around 1 micron. Let's consider like this. If someone has drawn with only 0.5 microns, then here electromigration will fail. All these things we have to take in care as per layout guide. So since we are layout guys, so we need to take care of all these things. Even though if you take all these constraints into your consideration, sometimes there is some chances to some chance to get some failures in post layout simulations. Most probably these post layout simulations will failure because of these capacitances and routing resistances and some coupling capacitances between the signal to signal. Most probably these because of these issues only some simulations will fail. So let's take one more example. There are two signals. Among these two signals, let's say this is some critical signal, and the guy who has run the layout up for this schematic, he didn't care about these two signals. He just routed these two signals, and once after completing the post layout simulations, designer seeing some coupling capacitance between these two nets. See guys, mostly these type of these are the main issues which are causing post layout simulation failures. So he's seeing more gap between these two nets. So then designer came to us and he asked us, guy, I'm seeing more capacitance between these two nets. You have to do some changes to get rid of this one. So then immediately the best solution is what we need to do is, first thing is we need to increase the spacings between these two nets. Okay, that is one solution. And second thing is, if it is a critical signal, then we need to shield this signal so that any impact from the other signals, it will not the main signal will not impact because of the other signals, because we are shielding this main signal with some other same metals. Like if the main signal is routed with metal 2, then the shielded metal is also routed with metal 2. And here we have some other signals. It doesn't matter like what are the metal or whatever the signal that we are routed here. The impact, whatever the impact that the signal is showing, that is completely on this only this shielded metal, and these two shielded metals are connected to the ground. So the total impact, that is only this shielded metal only will see the total impact from the other noisy signals. The main critical signal, it will not see any impacts from the noisy signals because it is shielded, right? It is covered with the ground signals. You understood, right?
Yes, sir.
Yeah, these type of techniques we have to use while drawing the layouts. So that if you know all these kind of techniques, the thing is it will reduce the iteration. Sometimes even it doesn't require single iteration also. Directly it will pass the post layout simulations. Okay. Understood, right?
Got it.
Hello? And one more example, if you take one differential pair, so here you need to match both these VGS. Correct, right?
Yes.
For this one, anyway, this is shorted, right? The source terminals are shorted. Forget about this. The thing is, you need to match these gate routings also. And also, you need to maintain some symmetricities between these output nets. Okay. So these kind of guidelines, if you follow for these kind of differential pair layouts, 100% definitely that kind of layout will pass the post layout simulations. But if you don't know these techniques, like blindly, if you place the devices as per your vision, if you complete the routings, definitely the post layout simulations will fail, and designer will come to us and he will ask to do the you have to change the layout and all. Understood, right? And again, there are some there are some other submicron, deep submicron process effects also there, like well proximity effects and length of oxide diffusions and STA effects. So these are deep submicron effects. That well proximity effect means, let's say PMOS will fabricate in N-well, right? So this is N-well. And if you fabricate mass transistor at the edges of this N-well, then it will impact the VT. It will impact the entire VT of total PMOS. Or otherwise, if we kept this mass transistor at right side edge, then this will also affect VT of PMOS. So if you want to overcome this well proximity effect, what the solution is, you need to fabricate the PMOS active transistor exactly at the center of the well. You need to maintain sufficient amount of space between the N-well edge to the PMOS gate. Okay. In our regular course, we'll go some in depth how it will impact the VT of PMOS if you place the mass transistor at the edges of the N-well. Okay. Similarly, if you kept NMOS transistors near to this N-well, then this also will impact the VT of NMOS. And same thing if you come to the LOD. LOD means length of oxide diffusion. Let's say if you have one differential pair, and I have used the common centroid matching techniques for these mass transistors. This is the active gate, and this is source, and this is drain. This is the active edge, sharp edge. Here we will have sharp edge. If you don't have sufficient space from the active edge to this active gate, then in fabrication, because of this active edge, there will be some mechanical stress. And because of these stress effects, this entire active gate will damage. So in order to protect this gate, what we need to do is, we need to increase the effective space between the extreme active edge to the active gate. For that, we need to add some dummies. So if we add some dummies, then ultimately that means we are increasing the effective space between active edge to the gate. So this is one kind of technique Understood, right?
Got it.
Again, if you come to the standard cell layouts, so the process of the standard, I mean the way of standard cell layout drawing, it's a little bit different compared to the analog layouts. See, in analog layouts, you will get this kind of instance by default from the foundry itself. This is source and this is drain and this is the gate. Say, let's say it is NMOS. You will get this layout by default. This is, you can call it as a P cell, parameter cell. But in standard cell layout, you have to design this cell itself on your own. Because in standard cells, you have to follow minimum guidelines. All are minimum spacings between metal to metal and layer to layer. But in analog layouts, it's not about the minimum spacings. You have to use at least 20% more compared to the minimum guidelines. Let's say there is one space between metal 1 to metal 1, the minimum space is 0.1. But in analog layout, you have to take 0.1 plus 20% more, at least, if it is an important signal. Otherwise, you can maintain 0.1 also. But it's better to follow at least 20% more. But in standard cell layout, you have to use 0.1 exact strictly. You should not increase anything. Okay. And even the cell pitch means cell height. Here, the total cell height is a fixed for all the cells. Like even if you take AND gate, inverter, or a D flip-flop or mux, whatever digital cells that you are going to draw the layout, the total cell height is always, it is fixed for all the cells. X you can vary. Depends on the schematic. The X you can vary. Okay. Hello?
Got it.
Yeah. So any questions till now?
No.
So okay, if I don't have any question, then I'll go to the next one. Like yeah. So till now we discussed about the block level layout, right? So if we come to the chip level, I'll show you how one chip will looks like. Let us consider this is one chip. So for every chip, there will be some boundary will be there. That is the chip boundary. So let's take it is a wide band chip. And again, in wide band, there are two types of chips will be there. One is inline and staggered. See, the difference between inline and staggered is it's how you are placing the bumps. Inline means all bumps will place in a straight line. Staggered means it's a zigzag, something like this. The bumps will, if you place bumps like this, it is a staggered. If you place bumps like this, it is inline structures. But there is one more. All these inline and staggered, these are the subtypes of wide band chips. And there is one more chip, like it is a flip chip. Flip chip means over the chip itself will have all the bumps, something like this. All these are the individual bumps. Bump means it's a pin. Okay, this is the basic structure of chips. And again, if you come to the inside of this chip, let's say first if you take one wide band chip, here you will get some multiple analog blocks like ADCs, PLL, and temperature sensors, something like there will be so many chips, so many core circuits will be there. To protect these core circuits, usually people will consider one IO ring. This entire thing is IO ring. See, this is one individual IPs, right? All these are individual IPs. Inside one, we have all individual IPs like PLL, ADCs, DAC, SUDDIS, data converters, and temperature sensor. So many blocks will be there based on the application. But to protect all these core circuitries, we should have some arrangements like some guard kind of thing. So that is IO ring. See, IO ring means there is one there in usually in companies, in almost all the companies, there will be one dedicated team to create all these IO rings. It is separate layout. There will be separate teams like IO layout teams. IO layout means actually these layouts will useful to protect the core chips from the ESD circuit, ESD phenomena. ESD means if any guy, if let's say if one human being touches one pin, usually all humans will contain some amount of static charge, right? So if you don't have some protection mechanism, so that static charge will pass to the core circuitry and it will damage the entire circuit. So to protect that one, we should have some bypass circuitry from the external environment. That bypass circuitry is the same thing. IO layouts, IO rings. Here we will have signal pads and power pads, pillar cells, corner cells, bias generators, and power clamps. This is entire different layouts. This is entire different team. In our course, I'll try to explain how about these layouts also. Okay, because I'm experienced in IO layout also. Currently, I'm working on this IO layout also. My present project is IO layout only. And in my previous companies, I worked on this analog layouts. Purely, it's core chips like PMICs, ADCs, DACs, and temperature sensors, something like that. Okay.
Will you cover this in somewhat in depth because this
Yeah,
is
so
usually not
see,
taught?
no, since this is a demo class, so I'm going briefly. But once if we start the regular class, I'll cover in depth.
Because usually it is not included in other classes like
Usually it is
curricular.
not included, but it's better to know about at least some brief information about the IO rings also.
Yeah, not only brief, but if you just take it in depth, I think, or like some other institution, it will be beneficial for us also. There it is not taught usually.
I have that curiosity to cover some extra cushion topics also. And that purely depends on the schedules and your interest also, right?
Yeah, correct.
So this is about the course structures. If you have any doubts about the course curriculum and what is the syllabus and duration, then you can ask me now. And also here, in the course duration, we will conduct some mock interviews also. So because it will helpful for you guys while you are appearing for the real interviews, correct, right?
Sir, I have one question.
Yeah, yes.
If there was a latch-up issue, then how oxide layer will be there's been changes or like that? Oxide layer will be affected or not, sir?
See, thing is because of latch up, oxide will not affect, but because of ESD, oxide will affect. But why people will consider latch up as a severe effect means latch up means there will be some continuous flow of leakage current will be flow from source supply to the ground.
Yeah.
Latch up means the meaning of latch up itself means there will be some virtual short will create. Some low impedance path will create from supply to the ground. It is not our intention, right?
Yes, sir.
Yeah. So see, guys,
That's when it will not affected. The one answer is it will not affect.
Oxide will not affect, but there will be some continuous flow of leakage current.
Okay. Yeah.
And guys, actually in our course duration, Actually, I will took at least minimum 45 to at least minimum 1 hour for latch up only. I will explain how in detail. I'll go in depth of like how latch up will trigger in terms of majority carriers. I'll go in that fashion, like how these carriers will move from source to supply to the ground. If you come to the P mass and N mass, how these carriers will move, how the leakage current will create, and what is the solutions to remove these latch ups and all. I'll both in layout perspective I'll cover, and even latch up, antenna effects, EMIR failures, and shieldings, STA effects, well proximity effects, LOD effects, matching techniques. Everything we will cover here.
Okay. Yeah, yes, sir.
What? Hello?
No, nothing. I was gonna say yes. Okay, yes.
Okay. Any questions regarding course structures and course durations?
For like EMI testing, I have seen like the different tools are used. Like one of that I have seen is
Yeah,
Totem. So will it be like is based on
it
that, or?
depends. See, it depends on company to company. So few companies will use Totem and few companies will use Voltas 5.
Okay.
Okay.
Sir, one question more.
Yes.
Sir, yeah, 45 nanometer technology, that's okay. But it will be like a TMCC, SCL, UMC, or GPDK. Which one, sir?
What? Can you come again?
Judgment GPDK 45 or TSMC 45, SCL 45, or UMC
It's a
45. Which one
GPDK.
will be?
It is GPDK 45.
Oh, okay. Yeah, okay.
Sir,
And see, yes. Tell me.
in 45 nanometer, what is the verification check?
DRC, LVS.
This
Those
one, sir.
are
I am asking about this caliber or Asura or PVS.
Ashura.
Asura, okay.
See, and guys, keep remember one thing.
Asura is not there now nowadays. Only caliber and PVS, right?
See, that's what I'm trying to tell you. See, as per my experience, I can say one thing. Blindly, I can say definitely there will be some difference between FinFET layouts and conventional masks. But as per my experience, guys, technology difference, it doesn't matter, guys. If you have some strong fundamentals in layout, technology, it's hardly 1 or 2 weeks. That's it. If you work two weeks or at least 20 days or something, then you people will get to know the differences between that old technology and latest one, and you people will get to know the difference between DRCs, and that is sufficient. And slowly, if you continuously if you work on the lower nodes only, then definitely you will get some complete understanding. But my best suggestion is you people should have some strong fundamentals. Otherwise, if you don't have some strong fundamentals, it's a waste of time to. I mean, even if someone has done some good experience in FinFET layouts, but he doesn't have some strong fundamentals in layout, I don't think he's a good layout guy. You understood, right? What I'm trying to tell? What is my intention actually?
Yeah.
See, even while I'm in my initial experiences, so till that time, we worked in only higher nodes like conventional mass. Suddenly, the entire industry is moving to FinFET layouts. So that is the starting time of using FinFETs. But we don't have any experience till that time. But finally, I mean, after spending some time, we completely understood what is FinFET structures and what is the impact of these FinFET layouts and that. Now it's it will not take much time, guys. And if you come to the reliability techniques like latch up, prevention of latch up, CMIRs, STA, LOD, these are common to any technology. Okay.
Hello, sir.
Yeah, yes.
Sir, actually, I don't have any experience with the same uh, field or something. So, do I need to prepare for something before joining this course?
So see, the intention of the course is itself that thing, right?
Hmm.
Here we assure you, like, after once if you complete this course, then you people will get some expertise in layout drawing. That we can assure you. But it's better, always it's better to have some basics, like basics about analog electronics and digital electronics.
Yes, sir. I'm from electronics background, so that is okay. So, other than this, it will be okay that I can join
Yeah,
with.
it's okay.
Mhm.
Actually everyone cannot get the tool exposure, right? So you never take graduation courses and all, right? So if you have some basics like related to electronics, like analog electronics, digital electronics, that is more than sufficient to start your career in VLSI.
Okay,
And
sir.
here actually the eligibility for this course is people should have graduation or post graduation coming from electronics background, ECE, triple E, or electronics and instrumentation engineering. That is a basic thing, right? That you might know, all everyone, you know, right? That's a basic requirement.
Yes, sir. Yeah.
So any questions?
Sir, actually, I'm working professional, so I have 4+ years of experience. So how can I switch from my for now I'm as a working as a component engineer for electronics design. So how can we switch from component to VLSI engineer or something? So,
Component engineering means what is the actual
sir, actually
what?
for hardware design, we are suggesting the alternates. Alternate components to check the parametric to check the to check parametric comparison uh, in the
Okay, tell me
form of
where you are working. Where you are working?
sir, in Veroc lighting systems, Pune, Chinswad.
What?
Sir, Veroc lighting systems.
Okay, understood.
Yeah.
Yeah, you can switch because you, at least you have some exposure about the industries,
Yes,
electronic
sir.
industries, right? Some people will join without having any experience, right? But now they are they understood everything in what is going on in industry and how to draw the layouts and what they understood all these concepts and all, right? Then I think we don't have any issues with that.
Okay, sir. Okay.
You at least you have some that much maturity, what is going what will be happening in industries and all, right?
Yes, sir.
Yeah, that is it's a good extra boost for you.
Yeah. Yes, sir. Okay.
I don't have any question, but I have like one request. Since you have like expertise in IO ring also and all this IO layout, I think it would
Yeah.
be my reinforcing point that I'm again iterating it. If you cover that, I think that will be like uh, beneficial for us.
See, don't worry, I'll try, definitely I'll cover, because in current batch also I'm covering that one. See, thing is, guys, my classes, how it will be is it's not completely depends on the time to time. Like I need to start class at 7, I need to close the class at 8. I will not take classes like that. I'll try to cover the concept completely. Either it can go it can extend up to 1.5 hour or 1 hour. You understood, right?
Got it. Got it.
Yeah. So my main motto is I need to cover the concept. You have to understood the concept, that's it. It doesn't matter about the 1 hour time or 1.5 hour time.
Will we be following any like some reference book or something like that, or not?
Yeah, here we will provide offline course material also, and actually that course material is it is very good one. You'll get some complete basics also. Even it's related analog electronics, digital electronics, even that kind of topics also we will cover.
Okay, but not any outside book or something. Just usually people do have a reference book. For like
Difference.
for circuits
See,
like there are, but for layout, I think though there is no like.
yeah, see guys, if you have interest, if you have your own interest, then I'll recommend few books. Because even while I'm in my gate preparation, I cover those books, and those books are so much helpful for me. Helped me a lot. And if you come to the electronic circuits, if you want to practice more circuits to get some more concepts, you know Kanodia books, right? Kanodia practice books.
Yeah, I mean, like for gate questions, I've like known those books, but question wise, but yeah.
Kanodia, and there is one book is that like Williams Hack. I forgot the exact name, but that name is
William Hyatt,
Hayat.
yeah, William
William
Hyatt.
Hayat or something is there. That book is very good for circuits.
Yeah, but
And
I'm
Jacob
asking like
Becker also
layout,
nice.
what layout?
Yeah.
layout perspective.
Layout perspective means there is one book, I think hacking something book, one book is there, but it is very calm. That book is a little bit tricky, guys.
Rajavi also nice.
Huh?
Rajavi, we had that.
Rajavi is for analog electronics, right? Yeah, there also you will get some information about the layouts, but it's a very good book for analog circuits mainly.
Yeah, Jacob Becker also is there.
Yeah, Jacob Baker, and all these books are very good for analog circuits, analog electronics. But for purely layout, there is one book, I think Hackins. There is some other. Yeah, actually, I forgot that name.
You can ping us later, maybe. Yeah.
Yeah, later I'll let you know. That book that is good for layout, but thing is, it will take too much time, guys. If you don't know any basics, then it will take a lot of time to understand the things. And even if you don't practice the layout, it will take too much time, because layout means it's a practical thing, right? You can't understand by theoreticalities.
Correct.
See, let's say if you know about the latch up in theoretically, but you should feel that in practical layout, then only you can understand. Oh, okay, if I place this device like this, then I will get latch up. So then immediately you will get some solution practically. Theoretical concepts are different, practical application is different, right?
Correct.
Yeah. Okay, guys. Any questions now? If you don't have anything, then we'll close this demo session.
Yeah.
Thank you.
Thank you.
Yeah. You don't have any questions?
No.
Okay then. So all are you are all working professionals or freshers also there?
I am a doctoral student. I'm pursuing PhD right now.
Oh, okay, great. Good to hear that.
I was with NVIDIA before in signal integrity team. Now,
Okay.
because of my work, I have to move to pre-silicon.
What okay, pre-silicon. Okay.
Yeah, before in NVIDIA I was in post-silicon, mostly in SI.
That's why you are asking about more information on post-layer simulations, sir.
No, actually, I'm supposed to design ASIC by end of my doctoral course.
Okay.
And I have to start from ground up.
Yeah, then I understood your intention, exactly why you asked post-layer simulations and all.
Yeah, so I would be having a mixed signal design.
Yeah, I understood. So here total 11 participants are there, with including me. So Kamaji, Sai Kiran, Netaji, Pankaj, Red. So your name, I think just now I talked with someone, right? Who is from PhD
I'm
background.
Suraj. Suraj is my name.
Suraj. Okay. Where you are doing your PhD?
I'm in Kyoto University in Japan right now.
Oh, it's good.
I did my master's in India from NIT Surathkal. So I did my master's in VLSI, but we weren't using the cadence. We were using open source tool called Magic. It's from UC Berkeley. So we did the
Okay.
same things that you just mentioned, but totally on a different tool.
Okay. Currently, in which domain you are doing your research?
Mine is into computer algorithms and into biomedics. So it's, how do I say, it's fusion of both.
Okay. So is there any other persons have some very good qualification like around PhD or masters?
I've done masters from IIT Roorkee, and currently I'm working in Samsung since last 1 year.
Oh,
So
you are working in Samsung. Actually, my
Yeah.
past company is Samsung.
yeah, I just checked your LinkedIn profile.
Yeah.
I think for 2-3 years you worked. Yeah.
Yeah, 2.5 years I worked there.
Yeah. So like since I'm fresher only, like last 1 year I'm working in industry. But I'm working currently like on tree simulation, and some a senior guy will be there who will be guiding in layout, and then I work on post sim, but I haven't really touched the layout part. So tree sim and post sim I'm doing, but not the layout. So I'm here to learn. Maybe in future it will help.
Okay, good to hear. I think you all guys have so much curiosity about the industry and all.
Sir, can you get your number like for colleague? Can you
What?
put your number, sir? You told na, sir, if you were in person, so ask you number. So personally call.
Okay, yeah, note it down.
Uh, uh, just a minute.
919121.
Just a minute, sir.
And guys, keep remember one thing. So I think few people has seen my LinkedIn profile, right? But don't tell anything like don't reveal all my work experience and all, because most importantly not about wherever I work there, right? So don't reveal those company names to anyone, because it will create some problems for me from my company side. You understood, right, my intention?
Yeah. Sir, please number.
Yeah,
Yeah,
got
9121
Yeah.
06
06
1612.
1612. Thank you. Thank you, sir.
Yeah, thanks. Yeah, someone is trying to ask something. So in Samsung, which team currently, in which team you are working, man?
IPD PSY.
IPD PS1.
PHY. Saturday.
Who is your manager there?
Avni Singh Verma, and the main manager is head of the HOD is Sanjeev Kumar Ghosh.
Okay.
Do you know them? Maybe.
No, I don't know him, because we are different, completely different business unit.
Yeah. Business in a city. Yeah. High speed Saturday city. Yeah.
You are working in high speed service.
Yeah.
Yeah, it's good. So it is Bangalore location or different location?
Bangalore. SSIR.
SSIR. It's near to Mahadevapura.
Yeah, correct.
Yeah. Recently, I just came out from Samsung.
Yeah, okay. Yeah. Mhm.
Okay, guys. Good to talk with you all.
Thank you, sir.
Yeah. Thanks everyone. Bye. We'll meet you soon.
Thank you.